Hello everyone, my name is Joosen and I'm a machine learning researcher at Huawei. And I'm also the first author of this paper, and today I'll be presenting serverless cold starts and where to find them. So first, I just want to discuss why we wrote this paper and what exactly is in it. So we're an industrial research lab of Huawei, and we work on improving Huawei's serverless cloud. We do a lot of analysis internally, and we also work with academics. So to facilitate that collaboration, we've decided to open source the data and also a lot of our internal analysis. So we've also written a previous paper 2 years ago, which released data that you may be familiar with. And people have asked if we can have multiple regions, if we can have cold starts, and if we can have event-based data. And so now we do have all of those things in our new data release. So now that we've released the new data set, the aim of this paper is to highlight some insights into parts of the data that we think are especially promising and that we hope will move forward some underexplored areas of serverless systems. So I'll briefly go over function as a service, which is a type of cloud product where developers write their application in terms of functions, and where exactly the function runs and other backend management is all left to the cloud provider. And so nowadays, all major cloud providers have a service like this. So you can imagine it pretty much as follows. The developer writes a function to do, for example, image classification, but it can really be any task. So once the user has written this function, you can give it inputs, and then it will be sent to the cloud to run in a pod, and then a response is returned back to the user. And so at Huawei, our FaaS service runs on a platform called Jianfeng. And so functions can be invoked by different events, so for example, timers, storage events, or even other functions. So functions are usually invoked many times, and the traffic of these requests changes quite significantly depending on the time of day, so many pods are required for a given function. The number of pods has to be determined by the cloud provider according to demand for each function so that the developer does not have to worry about these types of scaling decisions. So when there aren't enough pods to serve all of the requests, a new pod has to be started in what's known as a cold start. So there are several steps to a cold start, as you can see in the diagram here. So a pod has to be allocated, and then we have to deploy code and any dependencies if we have them, and then any scheduling or other overheads that we may have will also occur. So cold starts slow down our service, and we obviously want to avoid them wherever possible. So many papers have written extensively about how to reduce cold starts, but very few of them actually provide an in-depth analysis of where these cold starts come from. So for example, which functions cause them or which components in the system make these cold starts longer. So this is mainly because there are no open source data sets, especially from production, with detailed cold start information that researchers could use to answer these types of questions. So just to clarify again that if we have a running pod, then all of the individual requests are logged. So in previous data sets, we would have a timestamp, such as, for example, 6:35 p.m., and then the metrics would say that there were 5,000 requests in this given minute. And associated with that timestamp would also be an average latency and an average CPU usage that would represent the average of those metrics across those 5,000 requests that occurred in that minute. So obviously a lot of information is lost when that aggregation happens, but this is usually the format that exists out there. So what we've done is we've released a format of data that is shown here. So for cold starts, we've released individual cold start events. So we can see here the request ID. So this is the ID of an individual cold start. And each cold start has associated with it a timestamp, a request ID, but also many metrics, including, for example, the total time that's known as the cold start time, and then all kinds of component times that are listed afterwards. So the point here is that each cold start event is listed individually and can allow for much more granular simulations as a result. And so we have the same idea for individual requests. So each individual request comes with a timestamp and also a request ID, and then some other identifiers, and then all kinds of metrics that are defined more extensively in the schema, but things like how long it took to process the request, how long it took to queue and schedule, and so on. So this type of data allows for far more granular simulations compared to previous aggregate data that is currently available. So now we will discuss some of the insights that we think are particularly interesting from our data. So we'll analyze some similarities and differences between the 5 regions we have in our data sets and how we can use that for better scheduling. So this is a high-level overview of the sizes of our regions. So in total, we analyze 85 billion requests and around 12 million cold starts over the course of a month. So there are 5 regions in total, and they vary quite significantly by their amount of traffic. So now if we plot the cold start times of these regions, we can see some significant differences. So for example, we can see that regions 1 and 3 have similar numbers of requests, but their cold start times vary by an order of magnitude. So if we also plot the CPU usage, in addition to that, we can also see some significant differences between regions. So what we may be able to think about is there is an opportunity here to maybe move traffic between these different regions depending on how much demand there is and how much pressure each of these regions is experiencing at a given moment. And we are not balancing requests between regions at the moment, but that is something that is worth exploring given these differences. So additionally, we can see that peak times for our 5 different regions are different by several hours. So we can see here these red lines represent the peak times, and they are off between regions by quite a significant amount of time in many cases. So given these differences, it presents a significant opportunity for peak shaving and moving traffic to more off-peak regions. So another interesting finding is that very different functions are responsible for the number of cold starts, number of running pods, and number of functions. So normally we have this idea of popular functions that cause many cold starts because of frequent scaling decisions and unpopular functions that contribute less to traffic. However, we found that there is a lot more nuance in this aspect of the data, and that this is not always the case. So for example, timer-based functions make up less than 10% of running pods, but about 30% of cold starts, and over half of all of the functions on the platform. So another example of this is the custom runtime, which is responsible for only 3% of functions, but 10% of cold starts and 23% of running pods. So it's just useful to keep these asymmetries in mind when we optimize for a particular workload. So if we take the number of running pods we looked at previously and plot that over the 31 days of our data set, we can see a few interesting things. So normally, timer functions are brought up as a significant source of periodicity in these types of platforms. But in fact, we see that they are quite constant and contribute very little to the overall workload, while workflow and storage triggers contribute by far the most. So we can also split our workload by the size of the pods. so the resource configuration of the pods, and we can visualize it as shown here. So we can also see that pods of different sizes are requested in quite predictable patterns. And this means that we may be able to pre-warm pods of that configuration. And I'll discuss that in more detail later. So now that we've discussed which types of functions cause cold starts, we want to talk a bit about what causes longer cold starts. So here we show the different cold start components over time, as well as the number of cold starts. And so first of all, we can see that the different regions have different contributions from each component. So we can see this very clearly by studying the holiday period from day 13 to day 24. So that's roughly this period here on all of the graphs. So all of the regions experience it slightly differently, but they all have a visible holiday period. And so, for example, in region 1, most of the increase in the cold start time comes from scheduling and dependencies, whereas in region 4, most of that comes from pod allocation and scheduling. So the scheduling there plays a far more minor role. So what we notice is that these different regions would benefit from optimizations of different components because the dominant bottleneck due to either the workload or the architecture of that particular region is different. So now if we zoom in to a single region, we can plot the cold start time distribution per runtime language. So we can decompose this cold start time into its components, and what we see then is that different runtimes are bottlenecked by different parts of the system. So for example, we see that custom and HTTP runtimes are the slowest, and they are dominated by pod allocation time because a pod really has to be started from scratch for a custom runtime, while for HTTP, an HTTP server has to be started. So you can see also that for Go runtimes, the time to deploy code dominates, and there are many other examples of different runtimes being dominated by different components. So we've discussed quite a bit about cold starts, but we wanted to gain a more complete picture of the cost of cold starts beyond simply the cold start time. So after a pod is cold started, it would be more efficient somehow for it to have a longer lifetime compared to a pod that was deleted after processing only a single request. And so this may be especially relevant for pods with a longer cold start time. So in order to model this, we can define the pod utility ratio as follows, which is essentially the pod's useful lifetime divided by its cold start time. So a ratio of 1 or less here means that the pod is used for a time less than or equal to its cold start time, and a ratio of greater than 1 means that the pod has been alive for longer than its cold start time. So if we plot this pod utility ratio for different runtimes, we get the following plot. So what we saw earlier was that cold start times for custom and HTTP runtimes were quite large. But if we now look at the pod utility ratios, we can see that actually they perform better than some of the default runtimes. So what this means is that although the cold start times themselves are quite long, the pods stay alive for longer and likely serve more requests as a result. So in this way, we can get a alternative perspective on the cost of these cold starts, and particularly for pods with long cold start times, to see how long those pods remain in the system and learn a little bit more about their lifetime. So now that we've covered some of the insights from our paper, we will suggest some directions for future work based on our insights and data sets. So the first interesting direction is multi-region scheduling. So based on the distributions for latency and resource usage in our 5 regions, we think that there is significant potential in moving some of the traffic between regions depending on latency between data centers and latency criticality of the workload. So another promising direction is forecasting the number of pods of a given configuration demanded at a given time. So we saw earlier that demand for pods is very predictable and could benefit from some pre-warming. So this is something that we have actually implemented in production and has helped us save quite a lot of costs. So there are many other further work directions that are explained in more detail in the paper. And with that, I would like to thank you all very much for your time and attention and leave you with the link to our GitHub where you can access the dataset and code to work with it. Thank you very much.